Kia ora class, today we're going to run through a quick refresh of the 3 types of levers found in the body, plus we'll go over yesterday's work, one of the set tasks, in particular question 2. I know we have had a screencast on this before, but just to review the 3 different types of the levers, obviously in this diagram we have here on the right, we've got L, which represents the load, F the fulcrum or the pivot point, and E the effort. Obviously these are in the diagram here. We're going to put them to real life scenarios shortly, and obviously we want to transition through to the sport that you're doing your analysis on, for which most of you is badminton and some others golf. So we've got the first class lever. We'll go over that shortly. Most often seen, well, the only place really seen in the body is the neck joint. The second class lever, the second place that we'll see that will be mainly in the ankle joint, and then the third class lever we see is the most common type in the body as well. We've touched on the mechanical advantage of these 3 different types of levers, and we'll go into why there is a mechanical advantage in particular for the second class and not so much the third class, even though it is the most popular or common one in the body. Unfortunately has the least mechanical advantage. If you've read through, and part of yesterday's work was to read through the answers for Thursday's work around mechanical advantage, that will provide a lot more clarity around it, and you can obviously use some of that work when you complete your assessment for this. So next part we have is our load arm, and here it'll be represented as the load arm and the effort arm. Why we need to know these is that if one is longer than the other, that's when we start to get a mechanical advantage or disadvantage. By all means, you can stop this and read up on the left. I'll be summarizing each of these points, what's written on the left. I'll be summarizing on the right in the diagram. So the greater the ratio or effort arm to the load arm, the more efficient the lever system is. So we can see here, this is a second class lever. It does have a mechanical advantage, so in essence it can lift more with less effort than the third class lever we can see down the bottom here. So the gastrocnemius or the soleus connects to the ankle or the talus down here, tarsal, sorry, or the ankle bone or the heel bone. We've got the pivot point, which is right here, all right, in the mid part of the foot, and then we've got the load coming through here. So if we represent that in a diagram, the fulcrum is here, you can see it here, the load coming down through the middle of the foot is here, but the effort's here. And you can see that obviously if this was, and it can also be represented as say a wheelbarrow, the wheel's here, we can lift a heck of a lot of weight rather than the one below that we'll shortly go over, because we're lifting the weight here and the load's in the middle. If we were to go down to here, and this is why the ankle joint is one of the strongest ones, and we can see that when we're jumping off, we're lifting all our body weight and we're propelling it quite a way into the air. We can see down the bottom one, we've got the fulcrum on the pivot point, the elbow joint, and then we've got the insertion point for the bicep brachii right here. Obviously, for that to be more of an advantage, the point would be here. All right, and you can see that for common sense, we're going to have a lot more leverage coming from this point instead of this point here. However, we know that we've got most of the load down here. You can see from this diagram that the effort is quite close to the fulcrum, so mechanically it's disadvantaged. However, if the load is small, it can move that load quite fast because the load is further away from the pivot point. So the further around for angular momentum, we'll get to that, means that it can move a lot faster. And in particular, if we're holding a racket, again, that distance away from the point, which we'll start to call around torque, is a lot further away. So if we go into here, you can see slightly down the bottom, we have a little bit around, if I show you another example, we've got the load down here. If we lift, say, a heavy rock, we've got a little block in here that we're pivoting it on, and then we've got our effort arm, effort here, we're pushing down on this, and this is our load arm. And that there is somewhat similar in distance, which means that we can lift a lot more force. So we can lift more, all right, if this has got a higher mass or inertia, we can lift it. However, if it's the other way around, and this is a lot longer down here, then unfortunately we can obviously lift less, but we can move it a lot faster as we go through. So and it's got in here, to lift it, you would need to create a first class lever, a shovel and a cinder block. You strategically position your cinder block so that you would use it as leverage in the middle, and the shuffle hand rests on it. And then you push down on here, and it applies the force down here. And because these are equal, it means that it can lift a lot more weight. So if we were to go to how these are demonstrated in the body, the first class lever is the neck joint, right? And it connects to the head. And if this is demonstrated in badminton, would be demonstrated, say, in your movement. If you're looking at the shuttlecock coming down, you're pivoting this joint here at the neck, right? And you can see on this diagram, it clearly illustrates this is the load arm, this is the effort arm here. Effort's getting pulled down here by the neck muscle, right? And the load is your head. Your head weighs about 8% of your total body weight, up to sort of 6 kgs. So it's quite a lot of weight. And we know, and I've talked to you about this before, if your head pivot back, sort of where your head goes, the rest of your body follows. Even though it might only sound like 5 kgs, if it is out of proportion and not stabilized by the body, then it can affect stability and balance. So if you lift your head up too much to look at it, and your stability and your line of gravity, goes outside your base of support, it can mean that you can become unbalanced when we go through that. So that's where we see it in the body. It's the main point. You can read and pause on here to read some of that on the left. Next one down here we have is the third class lever. It is the most popular one in here. You can see it in the knee joint, many of the joints around the body, but we'll demonstrate it with the bicep. You can see that I've already described this to you. This is the fulcrum, the pivot point right on a shoulder joint, elbow joint. And here we have our biceps brachii in here, and then which is providing the effort. And then lastly, we see that the load is down here. So 50 pounds, for instance, a pretty big bicep curl is the load. You can see in here that this is going to struggle to lift it because the load arm is so long, right? And the effort arm, this point here, is so short. And you can see that if it was to pull here, and you can sometimes see it if I was to push a door open right by the hinge, it's really hard to do that. However, if I push it and increase the effort arm all the way out to the end of the door, it's a lot easier to push, somewhat similar to this diagram we've got in here. Obviously, you see this in badminton at your elbow joint, your shoulder joint, your knee joint, your hip, a lot of the areas where it flexes or abducts, you'll see this point. Lastly, you'll see this obviously in badminton. A lot of you should be jumping off the ground, or your expert is, and this is something you'll find that's quite different between you, is that we've got the pivot point, the fulcrum here, and then finally you've got the effort arm, goes all the way to the end, because it's being applied right at the last little bit of the bone, and this is your tendon, and then it's connecting to your gastrocnemius down here. Okay, so it's a lot more efficient at applying the force, and the load is through our body, down through the bone, right down here. So it's your body weight plus we're applying 50 pounds worth of load through there. So that's why your body can apply a lot more force, and hence why we can jump so high off the ground. So if we refer back to question 2 from yesterday, I was just studying how those levers presented or used, and how does it impact our performance, particularly in badminton. So first class lever, we've got in here, he's looking at the ball. Again, if this isn't managed well, putting on the neck, then that can affect his balance, because generally where your head goes, your body will follow, and obviously affect the line of gravity coming down through there as well. The next one is a second class lever. It's found as the ankle joint. You can see it here applying to the ground, and it's what's going to produce a lot of that force through the legs, applying through the ankle joint, and obviously end in the movement of plantar flexion. We can see that demonstrated here. And that's the place where we find the second class lever. So again, compare yourself. Have you done that well? And effectively compared to the expert, which we have demonstrated in this photo. Then where we have the third class lever, again, we find this in the knee joint, the hip, shoulder, elbow, and finally with the wrist, sort of a flick of the wrist that you can end with. Again, this is all force summation that goes through, but each of these combine effectively. And we looked at particularly the bicep joint here. Elbow joint, sorry, is it effective producing movement? We can extend on that because we have now a longer lever here, which we're shortly going to go over, which is the racket. As we demonstrated earlier, there is an advantage with the ankle joint or the second class lever being able to lift more weight. However, the third class lever can actually move the limb a lot faster. And in particular, this racket doesn't have a lot of mass associated with it, or inertia or weight. So we can move it quite quickly, and that's what we're aiming to do, to hit the shuttlecock as fast as we can. Obviously, that's through the range of motion back here, but in particular as biceps, if we have a long, it's advantageous or advantage to have a long lever when executing a shot or hit, in particular the badminton smash, by increasing the length of the lever. This then increases the range of motion at the lever's end, therefore increases the speed of the racket. And we've got in here, this is why it's recommended that the hitter and the person in this photo has a fully extended arm when they hit. And you'll see that he, even though it's a little bit blurry, will have a fully extended arm whilst performing this routine, because the principle of leverage states that the velocity, this is the speed of the racket and the direction it's traveling, at the end of the long lever, and that's the arm all the way through to the end of the racket, is faster than the velocity at the short lever, say at the elbow joint. It's going to be traveling a lot faster around this arc at the end of it, and that the end of the lever will move more quickly than any other point of the lever. And this is obviously, we can manipulate this slightly by holding the grip either closer to the top. The bonus with that is that we'll be a lot more accurate. When we see this in golf, the longer your driver, yes, you're going to have more speed as it comes down around that arc, a range of motion. But we unfortunately will have to contend with accuracy in there, which is a big part of it. When we're hitting the ball so far, if it's got a little bit of spin on it, and we're hitting it over 250 yards, that spin, by the time it lands, has impacted where it lands by quite a lot. This is why there's rules around how long a hockey stick could be, a golf stick could be, tennis, and obviously a badminton racket can be, because it's an advantage to have a longer racket. You can create more speed. However, being critical, there are disadvantages with it. In the final diagram we have here, similar to what you have, I've got a tennis racket here. You can see that the fulcrum's here, the force is applied here, and then the load. You often see this also in your elbow joint, your shoulder joint, all contribute. And a lot of the power you produce will be a flick of a wrist at the end. And you can see in this diagram here, the fulcrum, effort, and load is a third class lever. But we know, and what we talked about, it's going to make that racket go faster. It only has to hit a tennis ball, so the load which has to apply is quite low. And a shuttlecock obviously is a lot lower than the tennis ball. Our diagram here to the right, this is around the speed or angular velocity. It's a lot faster at A than it is C, because it's further away from the fulcrum or the pivot point, and that's what we want. We want speed in here. If we were lifting a rock, then we'd be using a different lever system to lift that rock up, because it would be lifting more inertia or load mass than hitting with speed, and that's where a third class lever is better and has more mechanical advantage to a degree.